Okay, today I'll present sampling-based multilingual alignment. This paper was contributed by researchers from France and presented at the International Conference of Recent Advances in NLP 2009 in Bulgaria. Firstly, let's look at the introduction of this paper. So the main purpose of this research is to develop a word alignment method by exploiting low frequency terms to extract high quality multi-word alignments. And then the method that they followed is random sampling of perfect alignments from different subcorpora. And they reported that the results were competitive with the standard alignment methods such as Giza++ in quality and also in lowering the processing time and generating more coverage corpora. So the motivation of this research is, as it is custom practice, the alignment methods are most of the time following the IBM models and implemented in Giza++. Most of these methods are based on SASTkul and high frequency methods. So this paper, the motivation of this paper is to use the low frequency features of a corpora in generating multi-word corpus with high quality. So some of the issues that are not in detail explored in other such kind of alignment methods include simultaneous multilingual alignments. Most of the time the alignments will be for bilingual alignments, and if you want to extend these methods, maybe you would have to use pivoting, but this paper in this research, it's possible to generate word alignments for any number of languages simultaneously. Another issue is scaling up and coverage, and also processing time. So some of the methods reviewed in this research had problem of scaling up or scaling down. When there is large amount of data, how is the performance affected by the algorithms? And when there is less amount of data, how does the algorithm become flexible to generate the required quality word alignments from this data? And also coverage. So when there is huge data, do you cover all the subparts of the data to generate the alignment methods? And processing time, as the complexity of the algorithms becomes more, then naturally the processing time will be also huge. So this paper addresses these kind of issues besides the quality. And finally, integration with real applications. If the softwares are not available freely, or if they are very complex and if they are not written in such a way that it can be integrated with other applications, then the practical use of these applications would be not so much. So in addition to quality, this paper also tries to address these issues. So what is the reason or rationale behind the shift of methodology from high frequency words to low frequency words? So our intuition is that high frequency terms have higher statistical significance. So in most of NLP or IR researches, most of the time the high frequency words are utilized for making statistical analysis. But in this paper, the different approach is the algorithm tries to remove some input data so that the frequency of the words will be lower. So the problem with this high frequency approach is, so assume that this is a corpus and there are high frequency terms and low frequency terms in a corpus. So if if we want, naturally, if we want to increase or to boost the performance of any system, then one of the approaches that is followed is increasing the data, so that more statistically significant information can be extracted from the data. So you increase the data, and then you get high frequency terms in the target data. But also, when you increase the data, along with the increment of these high frequency terms, there will be also some low frequency terms also. So again, the problem is not solved by just increasing the data, because high frequency words and then low frequency words will persist in the data. So it becomes like kind of vicious circle, increasing the data, and then there will be also low frequency words. So here the main motivation, as I have said, is why not use the low frequency words also to generate, in this case, word alignments. So this, so finding a method which would avoid this kind of indefinite data increment solution and trying to get safe alignment of low frequency words to generate alignments. So this is done by converting the high frequency terms to low frequency by decreasing the data from the corpus. Another useful phenomena which we see in this research is the use of Hapax legomena words, which means words which are found only once in their corpus, not necessarily in other corpuses, but in the corpus of the subject corpus. If those words are only found once, they are called Hapax words. So researchers show that a corpus could be 50% composed of this kind of Hapax vocabularies. So they, we can see that they constitute a huge amount of the corpus. So there is an assumption in this paper that Hapax words are aligned using equivalence. So if in the target and in the source sentence there are Hapax words, then it's highly likely that these words are perfect translations or perfect alignments to each other. So that's one assumption in this paper. So by filtering inputs or by decreasing the inputs, the high frequency terms are converted into low frequency terms, and the terms reduced to Hapaxes form translation pairs. That's the assumption, and these translation pairs are termed in this research as perfect alignments, alignments which are perfect to each other in meaning. So if we see the methodology, so as I've said, perfect alignments are sequence of words that strictly appear in the same sentence. So here is this is an assumption of the corpus. So we have English, French, and German. So these are the word alignments. So in this example, for example, there is this word one in line 1, and here also in line 3 we see the word one being repeated. So this information is regarding the position of the words in the corpus. So on 1 is found in line 1 and in line 3, and in both these lines it's perfectly aligned with this French word un. So same case also here with the German corpus, this einen word and this einen is perfectly aligned with 1. So this is what they mean by perfect alignments. This could be one word or it could be sequence of words also. So they generate these kind of relationships. And another concept is a lineal corpus, and from these relationships they try to generate a corpus which is a lingual, which means which is not a specific language, but a combination of all the languages which are discussed in the algorithm or in the system. So here, this is this one, we can call it subscript. It means English, as we can see here. 1 is for English, 2 is for French, and 3 is for German. So in this line, all the translation, the perfect translations are aligned. So this necessarily is treated as a monolingual corpus. A corpus, it's not actually monolingual, it's alingual. It doesn't represent any language, but it is treated as a monolingual corpus. So they start with this type of input for all the remaining processes. So this is the statistical or mathematical explanation of what the process, how to choose the alignments. So, there are probability values of which word to choose from the corpus, and which word is not going to be chosen, as we can see here. Which word has never been chosen, and which word is not present in the where the none of these in all of the sentences which is not ever chosen. So this is the formula that you have used to select data from different subcorpora. And while selecting, what they do is the huge corpus is divided into subcorpora. So there are decisions to make, like how many subcorpora do you need from the corpus. So this is the formula that they use for that. Number of random subcorpora of size k to create by sampling yields. So there are parameters for the number of the alingual corpus, the size of the alingual corpus, the size of the subcorpora, and the threshold for choosing a sentence from the corpus. So as I have been saying, new perfect alignments are created by removing input data, because once you remove the high frequency terms, there will be Hapaxes in the corpus. And sampling is random. So they have different subcorpora, and they randomly sample words from these different subcorpora. But doing this random sampling, as we will see here, their method ensures the coverage also. So they claim that the coverage is better than other traditional alignment methods such as Giza++. And the size of the subcorpora to process is given by this formula. So in order to include more sentences, or in order to improve the coverage, the alignments are extracted from different subcorpora. And because they are dividing the huge corpus into subcorpus, then parallel processing would be possible, so the processing time would be naturally lower. So we have seen these input words. This is the monolingual corpus, and by using this monolingual corpus at figure 2, the next step is to extract the words. So they extracted perfect alignments, which were found by reducing decreasing the size of the corpus, and not only perfect alignments, also their context would also be selected. So these are the alignments that we see here. So the frequency of these alignments is also counted here. So sometimes we see here that there is these non-contiguous word sequences, because some terms are missing here, one, and some term is missing, and please. So it's not always a contiguous sequence of words. So for selecting the candidate translations or scoring the alignments, the translation probability is computed between the monolingual or the alingual language and between a monolingual language and all the other remaining languages. So they consider one source language, and all the remaining languages will be considered as target languages. Although there is no source language relationship in this research, but in order to calculate the translation probability, one language would be considered as a source, and all the remaining would be targets. And in the next cycle, one of the languages from the target would be considered as a source, and they would calculate the translation probability again. So by doing this kind of analysis, then we will have many translation probabilities. So this considers F as a source language and the remaining are the target languages, and this is E as the source, and so on. So we have translation probabilities for every combination, one language and the remaining languages, and also lexical weights that we will see here. So this is an example, loud applause. This is an English word, and as we see here, it is aligned to French and German. So these values here are the highest values out of these combinations. These translation probabilities and also these lexical weights are the highest. So by maximizing, by taking the maximum of these translation probabilities and lexical weights, then they can say that these three languages are perfectly aligned, or this is the best translation that they can get from their system. So the role of the lexical weights, they are used as one of the distinguishing features in this research. So they determine the quality of alignments. These weights, they are used to evaluate the quality or to determine the quality of alignments. So evaluates how each source word translates into target word it links to. So the link could be between two words, or it could be between sequence of words. So one word in the corpus might be evaluated as a single word, or might be evaluated as a sequence of words. So the highest probability would be the highest probability values of translation probability and lexical probability would determine whether to translate the single word or as a sequence of words. So the final lexical weight would be the product of these individual translation weights. So for the evaluation, they tried to compare their system with the GISA++ results for two corpus. One is the IWSLT07 Japanese to English translation task, and another is Spanish to French corpus. So for the first one, as we can see the results here, the time taken for GISA to process the corpora is around 404 seconds, and the corpus contains 40,000 aligned sentences. So comparing with this reference result, and also here in their system, their system could run and it could be terminated at any time. So here this is half of the time that it took the GISA++ to process, and here the same time, and here we see that twice of the time. So as the time of at the time of processing of the system increases, that means more perfectly aligned sequence of words will be extracted from the corpus. So as we can see here, the results are here it is lower than the GISA++ because it processes for lower amount of time. And here, when the time is twice, we see that a little improvement is achieved from GISA++. So their system with the lexical weights performed in par with GISA++. And here we see also the coverage. So here the coverage is around 70%, but here the coverage was around 90%. And these are the entries or in the phrase tables. So we see both a decrease of processing, an improvement in the quality of alignments, and also an improvement in the coverage of the corpora that is being utilized for generating alignments. Though the sampling is random, but we see their technique has better coverage in these results. So similar also in the Spanish to French translation task, we see that the lexical weights improve the performance, and also the coverage is higher. So 67% and 86% coverage. So we see that there is a significant improvement of coverage. So here the result is a bit lower than the Giza++. So the quality, we can say the quality is almost similar to Giza++, but there are also other improvements. And the algorithm and the concepts in this algorithm are very simple when compared to Giza++. So the processing time also becomes lower. So in conclusion, the sampling-based alignment method allows multiple languages to be aligned simultaneously from parallel corpora. That's one of the issues they tried to solve in the beginning, doing simultaneous alignments for any number of languages. And also a unique feature or unique thing in this research was to utilize the low frequency terms. And in that process also the high frequency terms are converted into low frequency terms so that perfect alignments could be extracted from the corpus. And the sample-based approach produces high quality translation, as we have seen, and the method can match the accuracy of Giza++ while improving the coverage and also reducing the processing time. So that brings us to the end of this presentation. Thank you.